Good afternoon, students. In this chapter, in this video, I will be covering the last unit 3.6 of your chapter. This is a diagram, as you can see, is a picture of an alveolus, and in this alveolus, on one side, the blue colored cells are shown, that is the RBC, which indicates that they are laden with carbon dioxide. The blood flow in oxygen and it is high in carbon dioxide. Because it is low in oxygen, it is shown by blue color, and because it is high in carbon dioxide, we show rich oxygen cell as dark red colored cell. So this blood flows in the capillary, and because of the difference in the partial pressure of carbon dioxide and oxygen present in the capillary and the carbon dioxide or the oxygen present in the alveolus, it is due to the difference in the partial pressure that the exchange takes place, and capillary, when goes out of the alveolus, it is rich in or high in oxygen and low in carbon dioxide. The oxygen diffuse into the blood. The oxygen is picked up by the hemoglobin. The gases dissolve in moist mucus lining. Now, the respiratory process can be understood by examining the properties of the gases. As I have mentioned about the partial pressure of oxygen and partial pressure of carbon dioxide. So, we must understand what is the partial pressure or what is the gas pressure and the role of gas pressure in respiration. Gases move freely, but gas particles are constantly hitting the walls of their vessel, thereby producing a gas pressure. Air is a mixture of gas, primarily nitrogen, oxygen, water vapor, carbon dioxide. Nitrogen is about 79%, oxygen is about 21%, water vapor 0.5%, and carbon dioxide 0.0%. Each gas component of that mixture exert a pressure. Now consider gas, or we may say air, in a container, and in the container the amount of nitrogen is fixed. It will be 79% of what amount of air is totally present in that container. In that container, the percentage of oxygen will be 21%, water vapor 0.5, and carbon dioxide 0.04. So we know that each gas component in that mixture exert a pressure. The pressure for an individual gas in the mixture is known as the partial pressure of that gas. We know approximately 21% of the atmospheric gas is oxygen. And we have found out that the amount of carbon dioxide in that mixture is 0.04. The partial pressure for oxygen is much greater than that of carbon dioxide. The partial pressure of any gas is calculated by a formula. Capital P is equal to P atmospheric, that is the pressure of the atmosphere, into the percent content in the mixture. So, the partial pressure or the atmospheric pressure is the sum of all the partial pressure of atmospheric gas added together. To calculate P atmosphere, it is equal to partial pressure of nitrogen plus partial pressure of oxygen plus partial pressure of water plus partial pressure of carbon dioxide, and it comes out to be 760 mm of mercury. Partial pressure of atmosphere, or also known as the atmospheric pressure, is equal to 760 mm of mercury into percent content in the mixture. Therefore, pressure of atmosphere at sea level is 760 mm mercury. To calculate the partial pressure of oxygen, P, capital P in bracket, oxygen is equal to 760 mm of mercury into, we know that amount of oxygen in percentage is 0.21, that is 21% is equal to 0.21. It means 21 divided by 100, because when we say percent it is always in 100. So 21% means 21 divided by 100 and the value is 0.21. Therefore, partial pressure of oxygen is equal to 760 mm into 0.21, and it is 160 mm of mercury at sea level. Partial pressure of carbon dioxide is calculated by formula P in bracket carbon dioxide is equal to partial pressure of atmosphere into percent content in mixture. Atmospheric pressure or partial pressure of atmosphere is 760 mm mercury, multiply by, because carbon dioxide is 0.04%, so it means that 0.0004 into 760 mm of mercury. So, partial pressure of carbon dioxide is equal to 0.3 mm of mercury. At high altitude, the atmospheric pressure decreases because because at height we know that the temperature is low and the molecules are all scattered and the